Astronomers have made a groundbreaking discovery of an ultramassive black hole that's 32 billion times the mass of the Sun. This black hole is so huge that its event horizon, the point of no return for matter and light, spans a diameter that's 1,300 times the distance between the Earth and the Sun. This means if it were placed at the center of the solar system, its edge would lie way beyond interstellar space. The ultramassive black hole is located at the heart of a galaxy in the central region of a massive cluster, 2.7 billion light-years away from us. What's most remarkable is that astronomers utilized a never-before-used technique to measure the black hole's mass, marking a historic achievement in the field. So how did astronomers determine the mass of the black hole? How is it even possible to find the black hole's properties without actually observing it? Finally, and most importantly, why is this result so important for astronomy? Before we begin, I want you to look closely at this image. At first glance, it seems like an ordinary photo, but it reveals something truly remarkable. This stunning image captures a galaxy located around 10 billion light-years away and a cluster positioned approximately 5 billion light-years away from us. The arc-shaped pattern is due to the effect of gravitational lensing, where the light from a distant galaxy bends around a massive object with a tremendous gravitational field placed between the galaxy and the observer. The remarkable aspect of this image is that the arcs are not distorted pictures of different galaxies, but rather multiple images of the same galaxy. The light appears to be coming from multiple locations because it bends around the massive object and gets curved by its gravity. The massive galaxy cluster acts as a lens, bending the galaxy's light and producing these beautiful arcs. Gravitational lensing, a phenomenon first predicted by Albert Einstein in 1912, has become an essential tool for astronomers. It not only allows us to study distant galaxies and stars, but also magnifies their light. Because of this phenomenon, distant objects appear larger and brighter, making them more visible to telescopes. The discovery of Earendel, the most distant known single star, is a testament to the power of gravitational lensing, which can cause significant magnification factors. So lensing is astronomers' best friend, as it helps them to peer those regions of the cosmos which may remain hidden otherwise. Astronomers have made a remarkable discovery, highlighting the strong lensing ability of the brightest cluster galaxy, or BCG, in a massive cluster known as Abell 1201. A galaxy earns the title of BCG if it is the brightest one in a cluster of galaxies. This particular BCG is a CD-type galaxy, which typically refers to the most luminous elliptical galaxy found at the center of galaxy clusters. Informally, CD can stand for Central Dominant Galaxy. If you're wondering how astronomers found out about the massive black hole using the magnified image of another galaxy, all the clues lie in this image. First, let's focus on this part. There are three important things in it. The first is the central bright region. It's the CD galaxy in the center cluster, Abell 1201, which acts like a lens. The second is a giant arc seen at the top. It's the distorted image of the background galaxy. And finally, there's a smaller arc, known as the counter image of the same background galaxy. Now focus on the second column. These are the subtracted images in which the bright lensing galaxy is gotten rid of. This column only contains the two arcs of the lensed background galaxy. Finally, have a look at the third column. It is the magnified version of the counter image and lies at the heart of this discovery. Astronomers had discovered the primary arc several years ago by studying the gravitational effects on the motion of stars. The black hole's mass had been estimated to be around 25 billion solar masses, but later, astronomers found another arc, the counter image of the primary arc. Now the discovery of the counter arc is important because it is telling something truly remarkable about this system. An additional mass was required for the counter image to form so close to the central bright galaxy. Therefore, astronomers ran models of different masses to match the observed data. Observe these images from the research paper closely. The left column displays the model without a black hole, while the right column includes a black hole weighing around 10 billion solar masses. It is evident that the shape of the counter image deviates only in the presence of a black hole. The right column model accurately matches the shape of the observed counter image using Hubble. Therefore, the presence of a supermassive black hole is necessary to create the peculiar shape of the counter image. To determine the exact mass of the black hole, astronomers conducted additional simulations with various masses. The model that best aligned with observation had an estimated mass of 32.7 billion solar masses. Astronomers also established a theoretical upper limit to the mass of the black hole by running simulations with masses ranging from 0 to 100 billion solar masses. They found that once the mass crosses 53 billion solar masses, the distance from the central bright galaxy at which the counter image forms increases, and hence the model deviates from the observation. Hence, astronomers placed an upper limit of 53 billion solar masses on the black hole's mass. At 32.7 billion solar masses, this black hole is classified as an ultramassive black hole. Another notable aspect of this discovery is the novel technique employed to measure the black hole's mass. As previously mentioned, the mass estimate for this black hole was determined by studying the motion of stars surrounding it, a common method used in astrophysics. Other prevalent techniques involve analyzing light from gas accretion around the black hole. However, the mass measurement in this study utilized gravitational lensing, a less commonly used approach. This method proved successful, resulting in a more accurate mass measurement of at least 7 billion solar masses higher than the previous estimate. This groundbreaking discovery demonstrates the power of gravitational lensing and marks the first time a black hole's mass has been measured without the rare observation of a central image. The central image is one of the multiple lensed images of background galaxy that forms very close to the central object that is difficult to detect. That's because the brightness of the lensing galaxy outshines the faint central image. Furthermore, there exists a crucial relationship between the mass of a black hole at the center of a galaxy and the galaxy's velocity dispersion, known as the m-sigma relation. The graph depicting this relation shows black hole mass measurements obtained through various techniques, with the mass estimates and upper limit from this study indicated by a black point and a downward arrow. The mass-velocity dispersion relation for this ultramassive black hole falls within the 2 sigma outlier of the linear graph, indicating that gravitational lensing is a reliable method for measuring black hole masses. So the mass measurement of this ultramassive black hole highlights the significance of gravitational lensing and opens up new possibilities for detecting black holes, which will aid in our comprehension of the evolution of these enigmatic objects.